Good morning, everyone. I'm Stuart Carroll, and I'm glad to welcome you to the third in our series of Innovation in the AEC webinars. I'm joined today by Dr. Forrest Pfleger. Forrest has degrees from Stanford, MIT, and Harvard, and recently received his PhD from Stanford around this area of design optimization that he's going to present to you today. I believe that some of the ideas that Forrest has and will share with you are potentially revolutionary ideas and approaches to finding optimal project solutions. To some, it may sound like Star Trek type technology, but along the way this morning, Forrest is going to show you some real-world practical applications that he has conducted throughout his research and beyond. And I really hope you enjoy the presentation. Just a couple of quick housekeeping items and I'll hand it over to Forrest. So this is a webinar, meaning that we will not be able to hear any of your conversations directly. If you have questions, you can enter them directly into the GoToWebinar questions section, and at the end we'll reserve some time to actually answer those. And then we will record the webinar and post it directly after the webinar is complete. So if you wish to listen again or pass it on to others, it'll be hosted on our website. So without further ado, I'm going to hand it over to Forrest and take it away.
Thanks very much, Stuart, for the kind introduction. I do look forward to any questions that the audience might have as we go through it. I guess we'll address them at the end. What I wanted to present today was some research done in collaboration with some industry partners using a technique called multidisciplinary design optimization. The basic idea behind this is allowing the design team and the project stakeholders to specify a range of design options that they're interested in, and then using computational techniques to help search through that range to sort of present performance trade-offs and allow the team to hopefully make more informed decisions. So I'm going to just begin with some motivation for the research and then a couple of industry case study examples. We sort of tried to progress in complexity with the research. So the first example I'm going to present is in the structural domain, and then the second deals with multiple building systems with the idea of dealing with life cycle cost and carbon footprint. So just a little bit on my background aside from what Stuart mentioned on the educational side. So I'm actually a structural engineer by training. I worked for the engineering firm Arup in London for a few years before beginning the PhD, and this is just a sample of some of the structures. So basically very large steel structures, which kind of motivated the research, and I'll explain why just using this example. So there may be some structural engineers in the audience, but I'm just going to present kind of the basic problem that engineers deal with. So this is a large stadium roof space frame structure, and the sort of design goals in this case are economy, which is minimizing the steel costs or the construction costs. Usually in the early stages, you estimate this based on the tonnage of steel that you're using in the structure. This structure had an aesthetic component. The whole bottom surface of the truss is exposed to the crowd, so making sure that that met the architect's aesthetic criteria. And then, of course, we have constraints for safety, satisfying building code requirements for strength, as well as serviceability, which is basically how the structure deforms under load to make sure it's one, safe, and also comfortable for the audience. You don't want to see the roof flapping in the wind, for example. So from a design perspective, we're just going to restrict the scope to what's called member sizing, which is basically choosing cross-sectional areas for the 2,000 or so different members in the structure. So that can be things like tubes of varying thicknesses, square hollow sections or rectangular hollow sections, I sections, and most of the audience probably knows that these are manufactured in certain standard sizes. So from a mathematical perspective, we've got 2,000 or so different design variables, and with the architectural criteria in account, we've got about, say, 20 different cross-sectional choices for each member. So if you enumerate out all the possible configurations, you get a really large number there, e to the 2,000 scale, so millions upon trillions of different design options that are possible. And then here we have current practice. We shadowed the engineering team that actually designed, or at least performed the initial design on this stadium roof, and they looked at 40 or so different sizing alternatives before they settled on one that was feasible. So that took about 160 man-hours, so roughly about 4 hours per different configuration that they investigated. So then again, if we compare that to the design space, sort of my intuition in starting the PhD was, how general is the data in terms of how many options do engineers in practice typically look at, and two, what's the impact on quality? Given that in conventional practice we're really looking at such a small subset of what's possible, are engineers, do they have the necessary experience and skill to really be able to find the best designs given that small sample size? So again, we're going to focus just on structures for now. So this is a process map of the optimization method, but it's also a very similar process to the conventional techniques. So if we just look to the right here, we start with the geometry model. That is usually a CAD model that represents this sort of center line geometry of the structural members. So that could be tools like Revit or Rhino, or in this case we're using Digital Project, which is basically the CATIA engine that's made by Gary Technologies, because we wanted to take advantage of the parametric, being able to vary the geometry parametrically. So then we have next, the geometry is fed into an analytical tool. So this is typically a finite element solver, and that's used to sort of compute, given a certain loading, that's used to compute the forces and deflections on the structure. The next part of the process is what I'm calling the constraint check, which is you're comparing those forces and moments and deflections against the allowable criteria. So that's dictated by the building code in many cases. The client or the design team may have additional constraints that they're placing on it. For example, this roof had a limit on the amount of deflection that it could have in the middle of the arch to make sure that it wasn't perceptible to the crowd. So then, based on the sort of feedback from those constraints, we have two different design decisions to make. Should I go and change the configuration or member sizing? Or I could also change the shape of the structure, meaning the geometric dimensions. And finally, I could change the topology, which would be changing the number of members in the structure or how they're connected to each other. And so the optimization technique that was developed as part of my PhD basically divided this problem into two parts that are nested in each other. So we used one algorithm, which is shown in blue there, that design loop, called fully constrained design. So that was a sizing algorithm that I developed just to deal with member cross sections. And then the green design cycle is another algorithm that was used to look at varying the shape of the structure, and I'll explain just briefly why those algorithms selected as we go through a case study example. So this is the implementation of that, and I mentioned some of these softwares. So like I mentioned, we were using Digital Project for the geometry. The arrows here just represent data being transferred between the different software tools in the process. We used a tool that is in-house to Arup. Well, actually, it's commercially available, used largely by Arup, called Oasis GSA. That's a finite element solver, and then some custom scripts that check against the building code, as well as the optimization techniques that I mentioned. So let's go through how this was applied to this roof structure. So this is the results of that optimization process being applied. The left column is the conventional design process, and we kept track of sort of process efficiency metrics, which deal with how long it took to analyze a given alternative, what the setup time was, so how long it took before the first alternative was analyzed, and then the total design time. So what you notice in comparing these two techniques is that obviously the design cycle time is much lower in the computational optimization technique. The design cycle time in the computational technique is really just the amount of time it takes to run the finite element solver. The rest of the process proceeds very quickly. And in this case, we actually were able to parallelize the finite element analysis over a network of, in this case, like 16 servers or so we could get that down to near real time. So we looked at a much broader area of the space than designers typically evaluate. And you see that the setup time is significantly longer. So it took us maybe 2.5 times what the conventional process takes. That was largely basically writing some code that would integrate in the different analytical tools into that integrated process that I described. So that's using the API of these softwares, or what we call wrapping the input-output files. So there's a variety of techniques that we can use to sort of bring in common design or engineering tools into that integrated environment. And then you see the total design cycle time is actually less than the conventional process in this case. But what's more significant, I think, is if you compare the performance of the product, we're able to reduce the steel weight of the roof in this case by about 20%, which for a large structure like that is a significant financial difference. In this case, at the time, which was maybe 3 or 4 years ago, that was about $4 million in steel savings in US dollars. So, of course, it's natural to want to understand where these savings come from. So here is a rendering basically of where the steel is in the structure, both in the conventional design and in the optimized FCD design. So I'm going to try to explain a little bit about the design principles. So the engineers, when they're designing this process, when designing the structural conventionally, the sort of design philosophy was we'll make a very stiff rib along this leading edge, along the leading edge of the arch there. I'm not sure you can see my cursor, but along that leading edge. And so you see quite a lot of steel there on the sort of first bay of the truss. And then the structure will span from that stiff rib basically back to where it's continuously supported along the rear of the space frame. And then if you look at the FCD design, you'll notice that there's far less steel on that leading edge, and it's actually pushed some of the steel 2 or 3 bays back into the space frame. The reason for this, the reason why this is more efficient is because there's actually, if you were to take a cross section through the sort of apex of the arch, there's actually more structural depth back 2 or 3 bays. So if you think of this as a big truss spanning between 2 points, the deeper the truss is, the more efficient it's going to be. And so this basically makes it more efficient by making it stiffer further back where the cross-sectional area is the deepest. And you also avoid, if you look at the conventional design, you see there's quite a lot of steel on the supports there. You see a lot of orange, and that's basically because the structure was deflecting under the loads and it's fixed into concrete on those 2 supports on each side of the arch. And so it was creating a bit of a hinge in which there was a lot of bending that needed to be resisted. So there's a lot of steel to resist the bending, whereas if the arches were stiffer on top, it doesn't deflect as much, and therefore you don't have sort of local bending at the supports. So this was, this analysis was done retrospectively after the optimization is completed to try to understand why the structure was more efficient. And so just to kind of give you some background on the state of the design, the conventional design, the sort of baseline design, Arup actually was planning to submit to the contractor for bidding. So it was, a very finished design. The project got put on hold for a couple of months and gave us the opportunity to run the optimization. We produced this design that I'm showing you in the interim, and then Arup actually, in lieu of submitting their original design, they actually submitted the design that the optimization technique had generated to the contractor. And so that's, or close to that, is what actually got built, or is being built, I should say. So that's one structural example. We did a couple more as part of the research, but just to give you a little flavor of the sort of breadth that these techniques can be applied to, we're going to jump right to a multidisciplinary example. So dealing with the scope of services, interiors, shells, and substructure rather than just structure. So this involves a much broader segment of the design team or stakeholders. So as I mentioned at the beginning, the goal of this was to look at really early stage design and how do these decisions impact life cycle cost and carbon footprint. So here we have a diagram of the life cycle of a typical building. Raw material acquisition through the production of materials, through on-site construction, through the operational phase, including maintenance, repair, and replacement of building components, as well as utility costs over the lifetime of the building, and then of course demolition, which we didn't consider in this analysis, largely because there's a lot of uncertainty on what the sort of end-of-life scenario is for buildings, and not a lot of good information on sort of what the impacts of those are, so we left that off. Typically, that's a very small component of, say, life cycle carbon or life cycle cost. So I guess it's a reasonable omission on the building life cycle. This work was done in collaboration with Beck Tech, and I'll explain a little bit more about that as we go through the case study. But we were fortunate enough to be able to draw upon some of the industry projects that they were working on and the broader Beck company was working on, as well as some of the technology that they use, namely the deprofiler software, which some of you may be familiar with. So here's a process map of the different components that were integrated into the process. So they're color-coded according to the different softwares that were used, and I'm just going to walk through it. So we started with building information model. So that contains all the information about the geometry of the building, as well as, in this case, we used the deprofiler tool, which basically links a parametric representation of the geometry to a fairly detailed cost database. So we're using that tool to estimate pre-operational cost or construction cost. We used a tool called SEMAPro, which took in the quantities from the deprofiler model and had information on the embodied carbon in all of those materials in order to calculate sort of the embodied carbon portion of the carbon footprint. We used eQuest for energy simulation. eQuest is available. There's a link from deprofiler directly to eQuest so that you can run this type of simulation in your models. So we didn't need to create that link; it already existed. We have a tool called CostLab, which is a sort of web database available to owners. You give it some basic information about the building, and it computes operation, maintenance, repair, and replacement costs over the lifetime of the building. So that's repairing pieces of the mechanical system, repairing the facade, annual maintenance costs, all those type of costs are calculated in that program. Again, we use SEMAPro again to look at what is the carbon implications of the energy consumption during the operational phase and the maintenance, repair, and replacement phase. And then finally, the two yellow components in Excel are basically just spreadsheets that aggregate all that information in order to compute life cycle, carbon, and cost. And then finally, we have the optimization component. So that's iterating through all the different options that we're looking at to try to improve those two metrics. In this case, we used a multi-objective genetic algorithm, since we have two objectives here, carbon and cost. And I'm not going to explain the details of how that works. If there's interest at the end, maybe I can go into more depth about how the algorithm actually works. I'll jump right to the case study example. So this is an overseas housing compound that we were looking at. I'll explain a little bit. So here we see the compound actually had more than just housing on it. We were looking at just the housing component. So you see in plan here, here's the site. There's sort of a perimeter wall around the site, and there are 4 cookie cutter apartment buildings, which are 8 stories. 8-story buildings. And so we were going to vary some aspects about the massing and layout of these 4 buildings on site. So what the client was basically interested in was coming up with alternative designs that might be able to reduce the life cycle costs and or the carbon footprint. And they had a certain requirement for the number of apartments that needed to be present in the program. So we restricted the floor area to a constant number so that that would be respected. We did vary the number of buildings, so it could either be 3 or 4 buildings that would satisfy that requirement. The massings of those buildings could be between 5 and 8 stories. We sort of parameterized the generic footprint. So you can see on the diagram there, we used an H shape with 6 different possible variables in terms of how that shape is configured. We chose that because you can get a variety of shapes from this sort of generic footprint. For example, you can get a rectangle, you could get an L-shaped building, obviously you can get an H-shaped building, and a variety of others. So we felt that this was a general way to study potentially different footprints than the baseline design that you see. And then there were some interesting constraints as well, aside from just having a constant area. So one constraint was that the buildings had to be a certain distance from the perimeter fence, and that was for security reasons. And they also had to be a certain distance from each other, so 20 meters from the fence, 20 meters from each other. And then further incorporated in the analysis was there was a blast study done, which was simplified for our purposes to basically it drove spec for the glass on the facade as a function of how far the building was set back from the perimeter fence, as well as how high the windows were above the ground. And that actually turned out to be significant in terms of how the buildings were laid out, and I'll explain a little bit more about that as we go. So here's a plot of the results. This is kind of a busy chart, but I'll try to explain it. Each dot in this chart corresponds to a different design option. And then we have on the y-axis, we have life cycle cost, varying between roughly 165 million and 225 million. We have our carbon footprint in metric tons of carbon equivalent. And what you see if you look at, there's a black cross. That was the baseline design. So that was a 4-building, 8-story configuration. The colors of the dots correspond to basically the topology of the buildings. You can see in the key. So the blue dots correspond basically to 3-building configurations. The other colors correspond to 4-building configurations, varying between 5 and 8 stories. The gray dots are ones that didn't meet the layout constraints, i.e. they were not the minimum distance from the perimeter or from each other. So you see there's a fair amount of designs that were infeasible. So what's interesting when you look at this is obviously there's a whole swath of designs here that improve upon both objectives that the owner was interested in. And even more interesting than that is you see there's some red dots here which reduce the cost significantly compared to the baseline. So same massing but significant reductions in cost. And then you see if you're able to go down to a 3-building configuration, you're able to further reduce the costs. And I'll go through some sort of, we just screenshotted some actual examples of different dots in this space, and I'll try to explain where those savings came from as we just go through some sample designs. So here's the baseline, about 200 million in capital costs, and then there's the carbon footprint. What's a bit unique about these buildings is the colors of these charts correspond to how much of the cost is capital cost versus operational. So you can see in terms of carbon, the sort of embodied energy of the materials is roughly about 10% of the total life cycle carbon footprint, and that's typical for buildings in general. What's a bit unusual is from a cost perspective, usually the operational cost is kind of sort of more significant than the first costs. From a life cycle perspective, we're looking over 30 years in this case. But these buildings were actually, they're very sturdy buildings, and because of the blast requirements, they're actually fairly expensive. So first cost is driving a large percentage of the life cycle cost. So here's one of the designs. If you look sort of top right of this diagram, the orange dot highlights where this design is relative to the baseline. So this design is obviously the sort of same topology as the baseline design, i.e. 4-building, 8-story configuration. So where the cost savings in this case came from is, one, you can see the buildings are orientated so that the long faces of the facade are orientated north-south, or more north-south than they were in the original design. That makes the buildings a little bit more energy efficient and efficient to operate. As well, you can see that the buildings are actually sort of shifted to the left a little bit more than the baseline configuration. So this basically enabled the glass cheaper facade requirements because the blast risk was minimized. So to understand why that is, I'll explain a little bit. If you see the kind of the sort of east facade here, there's a road. The straight edge of the facade, straight edge of the site actually has a road near it. So the blast requirements had to deal with potentially a larger charge from a vehicle, whereas on the sort of north edge, the jagged edge of the site, there's a river there. You might be able to see it. There's sort of a canyon and a river, so the blast requirements were different. So you see the buildings sort of orientated themselves closer to that edge and further away from the edge where the blast risk was higher. So that actually enabled basically less panes of sort of lower spec glass to meet the blast requirements, which led to significant cost savings, as well as the operational benefits. So that's just one example. And then here are some others. So this is a 3-building sort of horseshoe configuration. So a lot of the savings in the 3 buildings configurations are somewhat intuitive in that the skin of these buildings are very expensive. The moment you go from 4 buildings to 3 buildings, you basically have less skin per unit floor area. So you have cost savings there in reducing the skin. And then in the operational, from an operational perspective, the climate here is pretty extreme in terms of hot and cold. So you have less sort of heat gain and loss through the skin because you have less surface area basically for heat transfer. So those are some of the benefits there for a 3-building configuration. And then here, just as a reference point, here we showed the cost minimum design. Admittedly, sort of, at least in the representation that we've shown, sort of boring from an architectural perspective. However, you know, what I want to highlight here is that I don't think where we're going with this technology is to just sort of have push-button design in which these techniques would just generate a design. Basically, you know, at least the way I view it is that these techniques are useful to help designers to sort of look at non-intuitive designs that might guide them or inspire them to look in other areas that they normally look. So obviously this is, the data is pretty good, but you know, there hasn't been much thought to the architectural treatment. So, you know, I imagine that an architect might look at some of the basic parameters of these massings and use that as a sort of jumping off point to begin sort of a more thoughtful design process on aesthetics and these sort of things. So I think, I mean, this is all so I guess before I finish, one of the interesting things is when you start looking at all this data, you know, you're looking at thousands of design options. How do you make sense out of all of it, and how do you sort of process this information as a designer to make it useful? So you might look at this chart and wonder how this sort of mess of lines helps you do that. And I think that there's a lot of work in this area in terms of visualizations, but I'll try to explain the sort of intent of this chart. So each different axis, vertical axis here, corresponds to either a different design variable. So you see number of buildings, number of floors, and then you see the 5 different building lengths and orientation. So those are sort of the design variables that we looked at. And then the last 2 vertical axes, we've got life cycle impact, that's carbon, life cycle cost. And so each different design basically is a polyline that passes through each of these vertical axes. Each of these axes has, you know, a range of possible designs in terms of, you know, minimum building length, maximum building length. And so the idea here is that you can trace any design through all of these axes, and I've colored them according to how well they satisfy the 2 objectives, life cycle impact and life cycle cost. So the colors there, the darker colors are the most efficient from a cost or carbon perspective. So if you trace those back through all of the different design variables, you can see basically the blue areas correspond to the ranges of each of these variables where there are efficient designs. So you can see a sort of range. In certain areas like orientation, there's this very small band where you get the most efficient designs. For other design variables, you have a sort of, like for example, building length D has sort of a pretty wide range of different lengths that are producing good designs. And so basically I just want to show this diagram as a way of ways that researchers are starting to explore how you look at these sort of complex multi-dimensional spaces to sort of guide you towards promising areas of the design space. So from a decision-making perspective, if I'm trying to decide which decisions to make, I might choose a decision, say, around orientation early on because I know I have a very small threshold to get efficiencies, whereas some of the other variables will accept a wider range and it doesn't impact performance as significantly. So this is just some ideas around how you might use the chart like this to sort of drive design decision making in the case that you can't make all these decisions at once. So here, this is just summarizing the process. Similarly to what we did for the structural example, you notice that for the multidisciplinary example in the conventional process, the design cycle time has gone up significantly. That's because obviously there's a lot of coordination that has to happen between various players to look at different alternatives. And so we have similar sort of comparison. In this case, it took us a little longer to set up, so we took a little bit longer in terms of the total design time. But as you saw from some of the designs, we were able to achieve, at least generate significant performance improvements in the design, or at least provide the design stakeholders with a good idea of the trade-offs between the two. So this is all that I had for the presentation. I'll take any questions that you might have.
Well, for us, we don't have any questions currently posted, so let's give everyone a few minutes. Type in their questions. Hopefully you'll agree with what I said at the beginning, that this is potentially revolutionary as it relates to our industry, and some may feel it's threatening, others may get excited. We'd love to hear if you have any questions or thoughts. Hey Forrest, whilst people are typing in questions, where do you think this will go with the industry, say 5 or 10 years from now?
I mean, what I was trying to hand at is I think that that actually, in order to make this more useful for designers, that it actually has to be something that's an interactive process. So I'm imagining that this technology or these tools will be something that the designers can sort of interact with in a very playful way, so they can sort of set up design problems in terms of, I want to look at the impact of orientation, or I want to look at the impact of these different site layouts. And using this technology and the fact that we now have computing that we can send a large amount of data out to the cloud essentially, and get a lot of computer processing power producing sort of analytical results, that we can leverage that to inform design. So I'm imagining designers be able to work with this and use these type of techniques as they need them, as they're engaging in the design process in a very sort of free-form way. So if they have a question about varying a certain variable, or what would be the impacts of different window types, that they can just quickly set up a problem like that and leverage these type of techniques to give them guidance. So like, I need to reduce my operating costs. Let's use these techniques to inform what design decisions are most significant on my operating costs, so I know where to focus. And then, if they're interested, what values of those design variables, give me the best designs, and they can use that as a sort of guidance to progress the design, rather than as a sort of it's a means to an end, rather than sort of obviously supplanting the design process entirely.
Do you think potentially this has the ability to change the way that architects are educated?
I do. I mean, I think that, aside from just architects, actually, so I've sort of gotten the perspective of both sides. Architects, I think, intuitively, they want to design high-performing buildings, and so having a tool like this that will give them sort of immediate performance feedback, I think that's, at least from the architects I've spoken to, that's what's most appealing to them, is the idea of getting instant feedback, whereas now, they have to pass this and design intent onto an engineering team who may take, depending on the fidelity of the analysis, may take, anywhere from hours to days to sort of give them information. So that's very attractive. And then, from the engineering side, engineers, they want to be able to interact, with the designers in step. So as designers are thinking of ideas, they want to be able to sort of input, their understanding of building physics. And so by integrating the tools in this way, they have to spend less time sort of managing that information flow, and they can spend more time creatively thinking about sort of design systems. But I guess one further comment on the educational side is it does take sort of different thinking than some architects or engineers might be trained traditionally. So, rather than thinking about a point design and learning from that and moving on to another design alternative in sort of a linear fashion, which is the way a lot of architects and engineers work now, to use these techniques effectively, you really have to be able to specify your design intent as a range of design options. I'm interested in this range, this segment of the design space, and learning to define that in an effective way to leverage these techniques, I think, is something that requires a little bit of training, so that I could see that impacting education.
Okay, there was a question about the software that you talked about, I believe, in case study 1. That you showed that you did alternatives in 30 seconds as opposed to 50 hours. And the question was, which softwares did you use?
So case study 1 being the structural example?
I believe so, yes.
Yeah, so the best slide for that is this one probably. So we used, in terms of the engineering and analysis tools, we used CATIA Digital Project as the CAD, parametric CAD tool. We used a software called Oasis GSA for structural finite element analysis. And then we used basically some custom scripts to check against building code requirements, as well as to program the optimization techniques. These scripts were implemented in a software called Model Center, which is developed by a company called Phoenix Integration. So this software basically is a way to create integrated processes amongst and this screen capture that you see is a screenshot of the software. So it allows you to pipe information between various applications and then automate that exchange and then automate the execution of design cycles. This software is used more commonly in sort of aerospace and defense industries for them to design different space vehicles or aerospace vehicles. And so it's commercially available. It's a bit expensive if you're not an academic, but that's the sort of framework tool that we used to run the study. I hope that answers the question.
Okay, another question and a similar one, Forrest, is, and I'll maybe make it a little bit more generic, but are any of the tools that you have dependent on solving a problem? So what I mean is, are there a variety of tools that you can use instead of just it has to be Digital Project or it has to be OAS, or can you use a variety of different tools?
Yeah, so basically these components are plug and play, right? So that if you wanted to use a different element solver or if you wanted to use a different CAD tool, you could. So for the implementation that we've done, basically the only requirements that you need in terms of the tools that you use are you have to be able to automate the tool, right? Which means the tool has to have an API where you can use commands to automate the input or extraction of information from the tool. And most engineering, design and engineering tools have that capability. Or the tool has to be able to be run in batch mode, which means you have an input and an output file, and you can specify a command that will execute the tool. So if you can basically, there's techniques that you can use to sort of wrap the input and output files, so you can change the values in those files or extract values, and then automate the execution of the tool. So if you can sort of automate the tool in one of those two ways, then that's really the only requirement in terms of the tool that you use. Of course, it has to be able to accomplish the function that you wanted it to, but I think that part, designers and engineers already sort of know the capabilities of these tools, so that's usually the reason for selecting a tool in the first place.
Okay, one other. So for the design exploration phase, how did you select the 39 alternatives to be looked at out of the total of 10 to the 2,435 options?
So I didn't select those. Those I was just shadowing the design team, and I was keeping track of how many options they looked at. So they were designing the process in the conventional way, and they chose the 39 alternatives. I was just using that as a baseline to compare these techniques against what was conventionally done.
Okay. Any other questions from anybody? I'll just give it a couple more seconds. All right, there's one other. So, let's see. Yeah, so the question is, let me kind of make it more broad, perhaps. So typically you use a piece of software for solving a particular problem. There's not a lot of setup. It sounds like with running these, there's a lot of effort associated with setting up and defining the problem.
Yes.
Is that something that you have to do every single time, or is it something once you set it up one time and you frame that type of problem, you can scale and use over and over again?
Yeah, that's a very good question. So the best way to answer that is so really difficulty in setting these processes up is when you have sort of new input types or output types, meaning, in the example of this, or say the second case study, the outputs that we're interested in are life cycle costs and life cycle carbon footprint, and the inputs were those varying things like orientation and the shape of the building. So if I had those same sort of questions, the same variables, but I had a different model, then the setup time is trivial. You just basically have to point it to a new model and start the optimization. Where the time comes in is when you're changing the definition of the problem. So if I were to decide, I really want to look at daylighting or some other performance criteria, then of course you've got to integrate in the necessary analysis tools to do that, and that's where the time comes in. But the idea, at least the way I would approach it from a sort of enterprise perspective, is you invest in sort of building out these capabilities, and then you develop a more general sort of tool set, so that then when you have a new project, you've already got the capability to do all these types of analyses, and you don't have to invest any time in sort of integrating the process, that you've already got those components and you can just plug them together and start work immediately. And so that's the strategy that the companies like Boeing and Raytheon that use these tools regularly, they basically have libraries and processes that they've developed, so that when they have a new project, they can just pull from their existing library and very quickly start running studies.
Terrific. Well, if there are no further questions, I'm sure Forrest will be putting words in your mouth, Forrest, but we're willing to answer them, follow-ups via email. You can get hold of Forrest directly through Beck, and we'll follow up with an email to everybody with contact information. And like I said at the beginning, we are going to post this webinar after the event, so if there's anything you wanted to check back in again, feel free. We'll send a link to everybody that's attended the webinar, and it will be on the same location on our website where the other webinars in this series are hosted. Next month's webinar will be also the second Thursday in August. It's going to be on laser scanning. It will be an overview of what's going on with laser scanning, where the particular type of technology is going, and its potential impact on other areas of the industry that are currently not employing it. So look out for that, and we want to thank you once again for attending. Forrest, really appreciate you taking the time to show everybody your work.
Yeah, thank you all for listening, and I'd be happy to answer any questions that we didn't address today. So thanks again.